In this particular derivation, we are going to derive time-independent Schrodinger wave equation. Using Schrodinger wave equation, we can find solution for simple systems. Okay, solution for simple systems can be obtained by solving Schrodinger wave equation. Okay, and this particular equation is derived on the basis of de Broglie wave hypothesis as well as few laws of classical mechanics. We are going to consider a simplest form of wave motion. Say, for example, a stretched spring which is traveling along x direction. Okay, so we are going to consider amplitude as omega at a point x. Okay, when the time is t. So for this kind of waves, okay, this kind of wave which is under consideration, its equation for wave motion is given by equation 1. Okay, del bar square omega divided by del bar x square, which is equal to 1 by b square into del bar square omega by del bar t square. Okay, so this equation represents the wave motion which we have considered. Okay, so from this particular equation itself, we can tell that the amplitude, okay, the amplitude of the wave omega, that is dependent on the direction of motion, okay, x, as well as the velocity of propagation v, and also the time. Okay, so from equation 1 itself, it is clear the amplitude of the wave is dependent on x, velocity v, and the time t. So where this omega now is a function of the displacement x and it is a function of time. Okay, so therefore we can write omega as a function of function of x and function of t. Okay, so omega, which is equal to f of x into f dash of t. Okay, which is denoted as equation 2, that gives the relation that omega is a function of x as well as it is a function of time t. Okay, where this f of x is function of the x coordinate only and f dash of t is a function of time only. Okay, so that is not interchangeable or nothing like that. There is no relationship between f of x and f dash of t. They are independently for x as well as for time t. Okay, so for the stationary waves, we have the function of time f dash of t is given by a sine 2 pi nu into t. Okay, where a is the constant value which gives us maximum amplitude and nu is the frequency of vibration, t is time. Okay, so for stationary wave, the function with respect to time f dash of t is given by a sine 2 pi nu into t. Okay, so this f dash of t we will substitute into equation 2. So we get omega is equal to f of x into a sine 2 pi nu into t. Okay, so that is done. Next, what we have to do? We have to differentiate equation 4 twice with respect to time. Okay, so keep in mind we are going to differentiate with respect to time. So the function of x, f of x, that will remain constant. Okay, we need to differentiate a sine 2 pi nu t. Okay, this term has to be differentiated where f of x will be constant. Why? Because we are going to differentiate with respect to time t. Okay, so double differentiation is needed. So here I have written in the pencil that gives us single differentiation. Okay, del bar omega divided by del bar t, where f of x is constant, that is written as such. Then in the term we have a, that is also constant. Okay, a is a constant. What we need to differentiate is sine 2 pi nu t. Differentiation of sin x is cos x. So this term differentiation, that will become cos 2 pi nu t. Okay, then along with the x we have constant term 2 pi nu. Differentiation of sin x is cos x into dx. Okay, so this will be cos 2 pi nu t, then that particular constant term 2 pi nu. So that is written here, a is a constant, then cos 2 pi nu t. So differentiation is done. This is single differentiation. We need to differentiate it twice. Again you differentiate this particular expression, del bar square omega divided by del bar t square, which is equal to, again the term f of x 2 pi nu, a is a constant, that can be written as such. Now what we need to differentiate is cos 2 pi nu t. Differentiation of cos 2 pi nu t. Differentiation of cos x is minus sin x, so a negative sign. Okay, then sin 2 pi nu t. Differentiation of 2 pi nu t, we will get 2 pi nu. Okay, so this expression will become, after double differentiation, we will get minus f of x 4 pi square nu square into a sin 2 pi nu t. Just to rearrange it, see, we have minus f of x 4 pi square nu square into a sin 2 pi nu t. Okay, so this a sin 2 pi nu t is nothing but the function f dash of t. Okay, from equation 3, this a sin 2 pi nu t can be replaced with f dash of t. Okay, so we get delta square omega divided by delta t square, which is equal to minus 4 pi square nu square f of x into f dash of t. Okay, this is denoted as equation 5. And next the task for us is to differentiate equation 2 twice with respect to x. We need to differentiate this particular equation 2 with respect to x. So we will keep f dash of t as constant. Okay, to do the differentiation once, delta omega divided by delta x is equal to delta f of x divided by delta x into f dash of t. Upon double differentiation, we will get delta square omega divided by delta x square, which is equal to delta square f of x divided by delta x square into f dash of t. This gives us equation 6. Now we have obtained two equations after double differentiation of equation 4 and equation 2, that we will substitute into our equation 1. Okay, so upon substitution, we will get delta square f of x divided by delta x square into f dash of t, which is equal to minus 1 by v square into 4 pi square nu square f of x into f dash of t. Okay, since we have f dash of t on either sides, we can cancel them each other. Then we are left with delta square f of x by delta x square, which is equal to minus 4 pi square nu square divided by v square into f of x. This gives us equation 7. Now you observe this equation 7, that is independent of the time factor. Okay, where previous equation we had one term for time or function of time was there in previous equations which we have considered in equation 1. Okay, now this equation 7 is time independent. Okay, it represents time independent variation of variation with respect to only amplitude. Okay, this equation 7 now is only in x direction. Okay, since we have considered wave motion only along x direction, this equation 7 gives us only x coordinate values. Okay, now we have this velocity can be related to wavelength. Okay, related to wavelength and frequency, which is given by v is equal to nu into lambda. Velocity is product of frequency and wavelength. That can be rearranged so as to get the ratio of frequency to wavelength, which is nothing but 1 by lambda. Okay, that we can substitute in equation 7. Upon substitution, we will get delta square f of x divided by delta x square, which is equal to minus 4 pi square divided by lambda square into f of x. Okay, now this equation 9, that gives us the wave motion along x direction only. Okay, in only one direction, but we need to consider wave motion in 3 directions. So what we will do, instead of the amplitude function f of x for one coordinate, that we will replace with wave function. Okay, this notation is called psi, psi. Okay, psi xyz or just psi, that gives us representation of amplitude along 3 coordinates or in 3 directions. Okay, so after writing wave function, okay, by replacing the x coordinate functions, okay, amplitude function f of x, that is replaced by wave function psi now. Hence we can write equation 9 as delta square psi divided by delta x square plus delta square psi divided by delta y square plus delta square psi divided by delta z square. Now this particular equation, which is on the left hand side, that gives us wave motion or wave amplitude or the amplitude function along three coordinates, okay, which is equal to minus 4 pi square divided by lambda square into psi. Okay, this is equation 10. Now this particular function, which is on the left hand side, that can be written as del square, okay, del square psi, which is equal to minus 4 pi square divided by lambda square into psi. Okay, this inverted triangle symbol is called del, del or nabla, nabla, del or nabla function. Okay, so del square is nothing but it is delta square by delta x square plus delta square by delta y square plus delta square by delta z square. This is called as Laplacian operator. Okay. So this is one of the operator of quantum chemistry or quantum mechanics, which is called Laplacian operator. Okay. So now we obtain equation for particles like electron, atom, molecules, photons, etc. Okay, that particular equation is equation 11. Now this can be applied to matter as well. Okay, so for that what we will do, we will apply de Broglie wave equation. Okay, where we have lambda is equal to h by mv. Okay, so we will include lambda is equal to h by mv in equation 11. So that can be written as del square psi is equal to minus 4 pi square m square v square divided by h square into psi. What we have done? We have substituted de Broglie wave equation for equation 11. Now we know that total energy of any particle, that is nothing but it is sum of the potential energy as well as kinetic energy. Let U be the potential energy, and we know expression for kinetic energy is half mv square, where m is mass of the particle, v is velocity. Okay, just do the rearrangement. Total energy E is sum of potential energy U plus kinetic energy half mv square. We will rearrange it and obtain what is the expression for mv square. Okay, so why this adjustment? Because we have mv square in our equation 2. We will rearrange the expression for total energy and obtain what is mv square. Okay, mv square is nothing but 2 into E minus U. 2 into total energy minus potential energy gives us mv square. Now this value for mv square will be substituted into equation 12, so that we will get del square psi is equal to minus 4 pi square divided by h square into m into 2 into E minus U psi. Okay, the terms on the right hand side that we will bring to the left hand side, we will get del square psi plus 8 pi square m by h square E minus U psi is equal to 0. Okay, this particular equation 13, that is called time independent Schrodinger wave equation, that describes the motion of particle with mass m under potential energy U. Okay, so now this equation can be applied to all the particles like photons, electrons as well as atoms. Okay, this equation 13, that is important, that gives us time independent Schrodinger wave equation. Okay, so now this particular equation that can be applied to a total number of systems, okay, whole lot of systems, and their solution gives us solution for that particular system. Okay, now what we do, we will just obtain another form of time independent Schrodinger wave equation. So what we will do, this E minus U, okay, that we will split this particular term into two terms, that can be written as del square psi plus 8 pi square m divided by h square E psi minus 8 pi square m by h square U psi is equal to 0. Multiply throughout the equation with negative sign. Okay, take the energy term capital E towards right hand side, so that term will become positive. Okay, 8 pi square m by h square into E psi. On the left hand side, we are left with minus del square plus 8 pi square m by h square into U into psi. Multiply with h square divided by 8 pi square m on both sides. Okay, After the multiplication, we will get minus h square divided by 8 pi square m into del square plus u, this whole term with the side, okay, which is equal to e psi. But this terms inside bracket, that is called Hamiltonian operator. So this particular equation 14, which is h psi is equal to e psi, is another form of time independent Schrodinger wave equation.